Today my talk is topic federation, enhance Kafka availability with sharded topics. Okay, let's get started. Here's the agenda of this talk today. So I'll briefly go over the Kafka ecosystem at Uber, and then we will look at the problem definition and basically the motivation behind why we need this federation. Then we'll get a little bit technical about we'll deep dive into federation architecture and look at a little bit implementation details. And we'll conclude with some forward-looking and Q&A. Okay. So here is an overview of Kafka ecosystem at Uber. So it sits at the core of our real-time data platform. And roughly, we can classify into two use cases, real-time pipeline or batch pipeline. For the real-time domain, it powers basically everything at Uber. For instance, our rider, driver app, or mapping and logistics. And for the downstream, it can be the use case, we power various use cases. Pops up as the most common use cases, right? Between inter-process communication, we have Flink as a downstream consumer to power real-time analytics. And also, it powers the Elk stack for logging, debugging purposes. And in the batch pipeline domain, we have Hive, Hadoop for periodic, batching jobs for analytics and stuff and whatnot. At Uber, we have one of the largest Kafka deployment, and to back up that claim, I'll just show you some numbers. So right now, we roughly process 17 trillion messages per day and persist about 10 petabytes per day. Right now, we manage about 40-ish production clusters, and which consists of about 10K hosts or brokers. Yep. This is a 10,000 feet view of the ecosystem. Don't get intimidated with these pictures. We'll spend some time to look at each component and try to understand the setups. So if you look at it roughly, we can classify it into 3 different domains, right? Data plane, control plane, and admin ops. So data plane, basically as the name implies, data plane is where the actual message flows, right? Where you're producing messages, you consume them. But we have a quite unique setup here because we have 2 proxy layers. You can see is basically hiding the Kafka infrastructure abstract them away from the users. So we have a Kafka REST proxy. This is a proxy for producing messages. And what's more special is we have a Kafka consumer proxy. So this basically changed the paradigm how messages are being consumed. As a native protocol, you're basically pulling from Kafka brokers, right? But in this innovation, we basically have a centralized services that consumes using native protocol from Kafka. But we are using gRPC protocol to push these messages to the downstream consumers. So it's kind of so there are a lot of advantages, why we're building this and what it offers. It's kind of out of the scope of this talk. We have a pretty well-written Eng block on KCP. If you're interested, you can go check it out. And we also have my coworker here who is a very expert in KCP. If you have heard it before, have some questions, you can find her after the talk. Yeah. Your replicator, well, what is that? So it's kind of like a mirror maker, but it's more like an in-house replication services we have at Uber. So as you know, at Uber, we have multi-region setups. And sometimes for analytics and other purposes, we may need a global view. So that's where this replication service comes play. Well, we replicate basically the regional data into a global cluster, right? And now we're looking at the control plane. we have two major pieces. So, and that's basically, we're gonna dive deeper today. That's basically the centerpiece that powers this federation idea. So one is the Kafka Ecosystem Manager. So this one is, you can simplify it just thinking of it as a enriched topic metadata storage, right? So anyone who have used Kafka before know that the metadata is stored in Zookeeper, right? But that metadata alone is not enough to power all these kind of use cases we support at Uber. So we need enriched metadata. For example, like you need to know who owns this topic, what's the tiering of this topic. So all this information, we have a separate storage. We call it KEM, we call it KMDB. And Discovery Service is basically built on top of this one to disseminate all this topic metadata information to the clients, right? So you need to know where to produce a topic because we have so many of topics, different clusters, and where to consume them. So for example, just for an idea, like an example use case, we have other things that can support by these setups. And the U-Replicator Manager basically manages how the replication service performs, what's the source and destination cluster to replicate the message. So this is basically, I think, I hope you have a little rough idea of how the setup here. Now, with that little understanding, we come to the problem like we're trying to solve with this topic federation. So as we manage this many of clusters and have different, have so heavy traffics, it's rare, but inevitable sometimes we may have run into like a cluster degradation, right? So one cluster is, let's say, completely down, the worst extreme case. Or for some reason, noisy neighbor and whatnot, it's causing that cluster to be slow, right? And in this case, it could trigger an outage and disruptive for a critical use case, right? And how do we tolerate this failure scenario? That's basically the focus of today, like what we're trying to address. And in this figure, you can see there are two failure scenarios where proxies failing or the Kafka itself is failing, right? So this could cause cluster level degradation. But there are challenges to solve this problem, right? So we maintain such a complicated ecosystem, so we need to still honor some user transparency. So the Kafka as an infrastructure team should bear the burden of maintaining or tolerating a cluster failure, but instead of let the users take care or affecting their day-to-day operation, right? We should abstract all these implementation details away, and also we should require no or minimum user efforts when actual issue happens, right, to mitigate. And also how quickly, how timely we can detect or mitigate this issue is very critical as well. So for some critical use cases, probably, let's say you're down 5 minutes, it could cause severe consequences. So the time is also a challenge here. And also, we need to take complexity into consideration. So yeah, we can try to build a perfect system, but it requires a lot of efforts to achieve that. It's not ideal, right? So our guidelines, like we try to make non-pervasive changes, and also we want to have an easy onboarding and rollout, right? We build a new feature, we want the rollout to be seamless and easy, right? So this brings to the solution we're proposing here today is the topic federation. So in a nutshell, it's just an abstraction, another abstract layer we introduced in our ecosystem that we treat a topic as a logical entity, and the logical topic can be sharded basically into multiple physical topics, right? This is similar like to tolerate a partition level failure, you need to have replicas, right, in Kafka. So to tolerate topic level failure, then you need replicas across different clusters. So this is basically the gist of this idea. Here, the figure basically is an example of the example topology. Like say you have a topic, but you have two replicas across two different clusters, and one is active and another is passive. So we'll dive into more possible topologies later, but this is just an illustration. So on a very high level view, so what we did is basically introducing this control plane, federation control plane. We abstract away all the details from users. And so the user does not need to know where the actual physics topics reside. For them, they only have one topic, right? The details they don't need to care about. Kafka as an infrastructure team take care of all the internal, all the management of topics and whatnot. But which begs the question, like, how do we do this? Like, two questions specifically. So how do we determine the topic topology, right? And where we store it. And once we have it, how do we populate these changes to clients? Let's say when they're upstreams or downstreams, when there is a issue or we make some change. Let's say we want to direct the traffic. Because the reason we want to have a replica is it will enable us to switch traffics, right? Let's say one cluster is down, then we switch the traffic to another. Now, how can we change this? How can we direct the traffic in like a real time or near real time, right? This is the two specific questions we're going to answer in the following slides. So in the KEM, so talking about how we build this topology is we treat basically topic as a logical entity, right? It has some generic properties like what's the topic type, who owns it, is this federation enabled or ingestion enabled? And then we have a rule-based topology generation that based on the predefined rules that we generate the actual physical topics or shards, in this case for federation, right? There's few example rules are listed in this topology, like a federation, how do we define federation, which cluster we use. We can predefine or allow users to customize it. Or what's the regional rule for this topic? Does this topic exist in one region or another or both? So there's all kinds of different dimensions, like how you define a topic. And what's makes it smart is like if you have another property, let's say another not federation, but some other property, you can just add a rule here, and then that will guide you how to generate these physical topics, right? Because at the end of the day, it's the physical topics that dictating the behavior of the producer or consumer clients, right? So for physical topics, for example, you will have more specific data for this topic, like more topic metadata, like what's the partition count, what's the retention hours, and whatnot. And the shard specs is basically specifically related to federation itself, basically linking the logical topic and physical topic, right? So because you need to know for this logical topic how many shards you already have, or how many physical topics shards you have. So the shard specs is basically a table in the database to provide this link. So basically connecting everything together. And I want to introduce like the traffic states like for the shards, right? As I mentioned earlier, we can switch traffic between shards, and then what determines which shard to use. So that's where the traffic states come into play, right? So there are 4 basic states for shard, excuse me. And the diagram shows the state transition. So you have active, warm up, drain, or inactive, right? For active, it's straightforward. So the shard is healthy. You can either produce to it and consume from it. And warm up is like and to transition from active to warm up, basically if you stop consume from this shard, then it's in the warm up state. So you can still produce to it, but there's no consumer from it, right? And from the drain states, let's say draining, basically you are draining the remaining traffic from that topic. So you'll be able to consume, but you will no longer be able to produce to it anymore, right? So to transition from active to drain to inactive, basically after, I think there's a typo here from the drain to inactive. So when you stop consume, that means you're already draining the topic and then it's becoming inactive, right? When from inactive, if you start consume, then it's basically you enter the draining stage. So this is basically controls or service to determine which shard is healthy to produce to. Let's say, and we have APIs or command lines. Currently, we have APIs. We are trying to build command lines to switch state, right? So you can set the healthy state of a shard to, let's say, inactive or something. Then basically you effectively switching traffic from one to another. Right? These are the possible topologies that we can support, but as I'll go over them, but some of them is probably not logically making any sense. But for the first one, I think this is the most common use case, is multi-cluster, right? Single shard per cluster. So basically you have a different shards across different clusters. And they could be active setup, active setup, or active passive setup. So for active setup, it's more like this basically enables you to do not only tolerating let's say, cluster failure or degradation. You can also dynamically routing traffics based on your actual performance, let's say latency, right, to two different clusters. Then you can do a kind of like a load balancing between different clusters, even though there is no, let's say, prolonged failure for a cluster. So if your goal is trying to optimize your performance, right? Or active passive is more like a passive backup. This is more for tolerating a failure. If the cluster is down, you can switch the traffic to the passive one, start producing, right? And consume from it. Single cluster, multiple shards. This is not like a very common use case, but it's kind of like a byproduct of this federation. So the way we manage topics at Uber is we set a cap on how large the topic can be on the same cluster. So single cluster, multiple shard can be naturally a solution to improve scalability of topics, right? Let's say your topic is exceeding the limit to the size of a single topic, but your organic traffic is still growing, right? So this can be a natural solution. You can have multiple topics on the same cluster to handle your organic traffic, right? Increase. Some other topologies like multi-cluster, multi-shards, active. This is so basically all the combinations you can think of, but not all of them like is in practice like reasonable to support, or does this make any sense? The customer is basically your user specifying, hey, I want 2 shards on these 2 different clusters, right? That's kind of like a very flexible. And you can determine, okay, you want active, passive. It's more like the kind of like a master key to, you can define any feasible topology that is supported. Okay, so with I think we covered enough of this KEM, so how we generating the topologies and the shard. So now the second question, remember. How we, if there's a change, if there's an incident, how do we switching the traffic? How do we populate this change state to client that, dynamically in real time? That's where the Discover service came into play. So we're seeing this figure again at the beginning of the presentation. Now it's just refresher memory. So Discover service sits in the center of the control plane, right? It is responsible for disseminating all this information changes, topic metadata changes. So we support the gRPC protocol, and the way we discover is per topic. We also support 2 modes. One is gRPC unary, and another is streaming. Where streaming is critical to support this dynamic update, right? And to promote wider adoption for this discovery or ease of integration, we create a dedicated client. And Golang and Java are 2 major languages or services that we support at Uber. And we have built-in error handlings. Also we decouple them from our producer client or consumer client. So even if you don't use, or you can basically use the Discover service as catering to your need. You probably only need to find out certain topic metadata information. You can utilize that. So you don't need to integrate it with a more heavy client like a REST client, which is the producer client. So if we zoom in to this Discover service, this is kind of like the major backend design for sending out real-time notification. So it's a streaming based. So the way we detect changes is we constantly pull from this KMDB, right, to detect changes. So every time we make, let's say, change a shard state, the change will be populating to this metadata manager. And once we find some changes, we'll queue it into the event queue and then send out to downstreams, to clients, right, using streaming. So then the bottleneck, how quickly we can react, is based on how frequently we pull from this database, right? So most of use case, we can probably send it to 1 minute, 30 seconds, or 1 minute or 30 seconds. That should be fast enough. Let's say if we have instant, we want to switch the traffic within 30 seconds, right? That's kind of like the guarantee or SLA provided to users. And the beauty of it is this: we don't need to involve users to do any code change or redeployment, because basically it's connected by the streaming connections, right? Once we have, we push the change to client will dynamically switching to produce to a different shard or consume from a different shard, right? This basically, and the observer basically is responsible for actually sending out those, handling some connection errors, sending out some notifications. So, and the client side, as I mentioned earlier, we have a dedicated discovery client. And the way we build our client is we utilize 2 different protocols, right? For federated topics, we rely on the streaming connection. But for normal topics not federally enabled, we'll just do a periodic, we just rely on unary gRPC, and then we have a background periodic refresh. The time could be much longer. Let's say we refresh every hour or a day or something. So just as a fallback that we make any change to topic metadata, which will be rare if the topic is not federated, right? And all the initial discovery is done from unary gRPC. Yeah. And only when, so basically this one also these two different protocol support also allows us to switch topic from federated or to non-federated. Because you have a periodic refresh, right? Unary gRPC to fetch this topic metadata. And let's say if in the next fetch, you find out, okay, this topic is being federated now. Then you will dynamically create, the client will dynamically create another streaming connection to listen to further updates. So treat it as a federated topic. And the same, like, so when you have a streaming topic and when you defederated this topic or set it to false, then it will basically clean up the federated states and shut down this background streaming and whatnot from the client. So this one basically allows you to dynamically change a topic from federation or non-federation. But the time will take some time. It's not real time, right? Because enable federation or disable federation does not require real-time change. Basically, you already onboarded, say, a topic to federation. Only when you switch shards, that's where the timing is critical. Right? And a few caveats for handling the streaming connections that we run into practice, some issues we run into in practice is client side, like, so we have connection errors, right? You have occasional disconnection, so we need to be able to handle auto reconnection with some exponential back-off retries so we don't overwhelm the server. And from the server side, we may have some stale connections, right? It could be closed because basically we cache them as an object, right? And the client could already be closed by client, but the server does not know. So one way to clean this up is we can have a regular forced metadata update to the client, right? So basically, it's an opportunity to examine whether this connection is still open or closed. If you run into error, you can simply shut down from the server side, because the client side has auto reconnection mechanism. So you either reconnect or basically is dead. And connection hotspots. So how do we try to avoid that one server host has too many streaming connections? So basically, we have a routing proxy in-house. It supports load balancing during the initial connection phase, but not after, right? So in this case, we can periodically disconnect the connection from the server side and let the client side to reconnect. So that will naturally balance out the connection counts on the server side. I think that's basically the kind of like the heavy part of this presentation. Just a recap of what we talked about is the scale of Kafka at Uber and the ecosystem that we have. And then topic federation basically is designed to boost this topic availability with replicas across different clusters, right? And we have this streaming mechanism in Discovery Service to update the downstream or upstreams in case there is a failure. There's some future works that we will be working on is like supporting different federation topology. So right now we support custom, but most of the common use case is the single shard, multiple cluster, active passive setup, right? There will be, like say, active, as I mentioned earlier, if is a good mechanism to kind of balancing between two different clusters based on the runtime, let's say, performance of different clusters. And also, from the client side, this comes hand-in-hand with this active setup. So if we have an intelligent client, we can route the traffic to different shards more intelligently, right? Performance-wise, or latency-based, and maybe other performance metrics based. And also, we need to support. Now, most of the switching is done manually. So we basically, for one topic or a few topics, we can run a script and redirect traffic to another cluster. But in the future, we're looking at to have automatic traffic drain or detection. So no manual work will be involved or less. I think that's all of my talk, and I'm ready to take any questions. Thank you.